Welcome again. Let's talk about symmetrical ketones now as it pertains to the aldol reaction. Although ketones are not the same as aldehydes, we will refer to this type of reaction still as an aldol reaction. And there's a couple of things that we're going to have to consider as it pertains to ketones specifically. The easiest situation that you could encounter is the one where the ketone that you're dealing with is symmetrical, meaning that the left side of the ketone from the point of view of the carbonyl is the same as the right portion of the ketone. So you do have two positions that have alpha hydrogens, but they are equivalent to each other, so it doesn't really make a huge difference as far as what's going to happen right here. So the event is going to work out similarly to what we did with the aldehydes. And just to refresh you on the technique, you want to label from the carbonyl carbon to the carbon that you're about to deprotonate to make the corresponding enolate. You want to label those two carbons numerically. And for the second ketone, you want to label starting from the carbonyl carbon and going all the way out to the longest chain. You want to label those carbons as well numerically. And so in this case, we're seeing a total of 5 carbons. So what you want to do is, as far as determining how this product is going to look like, right? This is done under base, just like the aldehydes. You label your 5 carbon chain, and then you start placing your substituents or functional groups in it, right? So a position 1, we're going to have still the carbonyl, right? Initially we form the enolate, but then that enolate reforms the carbonyl to undergo the condensation reaction. Now position 2, position 1, we have one more thing to consider. We have an ethyl group, right? So we have the carbonyl, but we also have this ethyl group here on the right side, so that ethyl group still has to be there. At position 2, we're going to have the methyl group that is present right there. And as we continue downwards, right, at position 3, we have another ethyl group that's sticking out from position 3, so we will have to have that in addition to what now is going to be an alcohol, right? So this is where the attack takes place in the condensation. So we'll have the alcohol, but we'll also have that ethyl group that they're both connected to position 3. And then at positions 4 and 5, there's nothing coming out of them, so they will be left exactly as they are. All right, so that's generally how this goes. It's not too bad when the ketones are symmetrical. Another situation that you could encounter that makes things rather simplistic is if your ketones only have one type of alpha hydrogen, right? So in the first example, the alpha carbon here on the left does have hydrogens, and so does the one on the right. But you could have situations where the ketone is not symmetrical, technically speaking, but the carbon here on the left, does have hydrogens, whereas the carbon here on the right does not, right? This is a quaternary carbon, so it doesn't have any protons on it. So the reaction will still kind of happen the same way, right? You only deprotonate the alpha hydrogen, and you only have really one choice as to where things are gonna be deprotonated from. So yes, the lack of alpha hydrogens on this group means that this is just gonna serve as a substituent for all intents and purposes. So you do the same thing as what we did here. You label your carbons. For the one that you're about to deprotonate, start with the carbonyl carbon, position 1, then position 2. Then jump over to the other ketone, start at the carbonyl carbon, so that's now position 3, and then make your way towards the longest chain, which means that in this case, again, we have 5 carbons to account for in total. So you start by writing the chain, the 5 carbon chain. Yeah, here we go. So little I got a little carried away right there. So you have the 5 carbon chain right here, and I drew it a little bit funky, mostly because I was about to run out of space, but you'll see that it's going to work out pretty soon. So first things first, at position 1, we're going to be reforming that carbonyl after the condensation, so we will have that double bonded oxygen component. But we also see that at position 1, we have technically a T-butyl group attached to it, right? So we will have to place that T-butyl group over on that position. And going around a position 2, you have nothing else sticking out of it, so position 2 is going to be free. position 3, we have a couple things. First of all, this carbonyl is going to be turned into an alcohol ultimately. But also position 3, we have a methyl group sticking out, right? So we will have that alcohol and we will also have the methyl group. And now you can start seeing why I drew this kind of in a funky way. And then finally, at position 4, we have 2 individual methyl groups arising from position 4. So position 4 will have to have those 2 methyl groups as well. And once you do this, then you got the entire condensation product of this reaction. Now, mind you, both of these products are under the assumption that you are not heating up the process to high temperatures. If you do, then you will undergo the E1CB elimination to produce the enone derivatives. So just be mindful of the conditions. All right, so yeah, the T-butyl group, although this is a perfect example of being a quaternary carbon, another good one to keep in mind is a phenyl group. A phenyl group technically will give you a quaternary carbon that doesn't have CHs. So those are things that you can use to, prevent your aldol reaction from undergoing multiple pathways. And what that brings us to is the case where the ketone happens to be asymmetrical. So in these cases, you have multiple things that could happen. So right here I'm showing you 2-butanone, and the carbon on the left is a CH3. The carbon on the right is technically an ethyl. So you have a CH2 versus CH3. The point is that they're not the same, and they will lead to 2 different products ultimately. So I'm highlighting them, in blue and red on purpose. Now, one thing I want you to notice too is that the carbons right here, or the H's rather, the one at position 2 is a lot more roomy. It is not as bulky or sterically bulky as what we have here on the opposite end of the molecule. So we'll play with that in a second. All right, so what I'm going to do right now is concentrate on this blue hydrogen and do the same thing we did in the previous examples. Label the carbonyl carbon where the enolization is about to happen, move over to the carbon where the deprotonation will take place, then jump over to the other carbonyl and go from there to the longest chain. So that gives us 5 carbons in total. All right, so if we only consider the proton for the time being, what will happen is that you'll have your 5 carbons, you will label them, and then you start the same process, right? So at position 1, we will still end up with the carbonyl. At position 1, we also have this ethyl group sticking out, so we'll have that ethyl group sticking out right there. At position 2, there's nothing else present. At position 3, we do have the carbonyl that's about to become an alcohol, and we also have this methyl group sticking out. So position 3 will have the alcohol and the methyl group. And positions 4 and 5 don't have anything else, so they will remain exactly as you see them right here. And that will be the direct immediate product. Once again, if you are heating this up under strenuous reflux conditions, the elimination route will take place and you'll get the enone, but at least this will be the immediate direct product. All right, now, if we consider the other proton, the one that's more sterically encumbered, then the numbering is going to change for this molecule, now moving towards the right. So we start with carbonyl like we did before, but now we move towards the right to account for this different hydrogen. And then we do the same thing. We set up the 5 carbon chain and we start placing things where they fall. So at position 1, we will have the carbonyl present, but we also now have this extra methyl that is stuck to position 1. So we'll have to have that methyl group in there. At position 2, we also do have an extra methyl that sticks out from it. So position 2 will have to have that methyl. And then by the time we get to position 3, we'll be forming that hydroxyl group, but we will also have a methyl group that's both of them attached. They're both attached to position 3. So we have the hydroxyl and we'll have that methyl. And then positions 4 and 5, nothing's attached to them, so you skip them the way they are. And if you look carefully at them, you should realize that they are different molecules. The bottom portion is identical, so don't let that fool you. The difference happens here on the top portion, right? Here we have 4 carbons in a row before you link to the next molecule, whereas right here we have 3 carbons in a row before you link to the next molecule, so that you are dealing with different molecules altogether. And at least under the sodium hydroxide conditions, you would get both products. Like you would not be able to avoid making both products. So here's where you want to think a little bit about how you can tinker with your conditions to favor one deprotonation versus the other, and by direct consequence, favor one final product over the other. So I mentioned this to you a little earlier. The hydrogens here on the left side, this is technically a primary carbon, so this is the less substituted hydrogen, alpha hydrogen, from the two options. And what will favor the protonation of this hydrogen is if you use a very bulky base, because the bulky base will be very preferential uh, over which side it deprotonates. The more bulk around the proton to be deprotonated, the less likely the bulky base is to attack that proton. So a bulky base will totally favor deprotonation here. So lithium hexamethyl disilazide will be a good choice, especially if you cool it down. And I would tell you right out, yes, you do want to cool this down. That will allow you to deprotonate the less substituted hydrogen and lead to the corresponding enolate. And then that will lead you to the product that we already derived in the previous slides. But let's say that you are interested on the proton right here that is more substituted. Well, what will help you out there is to use smaller bases, right? So if you stick with like lithium amide or even lithium hydroxide, right? I mentioned that you're going to get both products with hydroxide, but you will still favor the more substituted deprotonation because it forms the more substituted enolate. Um, Now that said, it will still kind of be a mixture, right? So this might not be per se the best strategy to make this particular product in the best yield available. To address that point and that issue, what we can do is something else I'm about to show you. Now, first, I want to remind you, however, that in order to form the enolate, the one that is less substituted, you do this under low temperature conditions with a bulky base, and initially you dissolve that bulky base in an inert solvent and you cool that down in a dry ice acetone mixture. After that, you add your ketone slowly so that you don't have too high a concentration of ketone at any given time. And if everything goes well, then you will produce selectively and quantitatively your enolate of choice. After that is when you'll add your second equivalent of ketone, and then you let this warm up to react. So that's usually how you would do this type of reaction. Now, the only potential issue that you could still encounter is that because you're still dealing with different type of alpha hydrogens, when you start warming up the solution for the condensation to occur, you could actually undergo an equilibrium where the protons get shuffle, right? Because this thing can act as a base and remove the proton of the alpha position of the more substituted site and lead to the other enolate. So this can definitely happen, and it's a potential problem that you have to be aware of. So pretty much hydroxide or the amide bases by themselves, they're not super duper selective because you have these problems as a result of how the procedure needs to go. So the way to really fix the problem is to, yes, use a bulky base at low temperature to make the less substituted enolate. But once you make that less substituted enolate, instead of bringing the ketone, you instead bring trimethyl chloride and you trap the enolate in that fashion. So this is an enol ether. And then you bring your ketone along with a Lewis acid to efficiently allow the condensation to happen. Likewise, we'll do the same thing with a more substituted carbon, but first let me show you how this mechanism works. First, you will deprotonate the less substituted alpha hydrogen, right? You produce your enolate, and then that lithium enolate simply is introduced to trimethyl chloride, and for all intents and purposes, this is technically an SN2 reaction, right? The oxygen is going to be the one that attacks silicon, and chloride takes off to give you the enolate right here. And at first you might think, well, why is that even happening? Why is not the carbon doing the attack? And the reason for that is because the bond that you form between silicon and oxygen is a lot stronger than the one you form between silicon and carbon. So you have that driving force, like really allowing the oxo group to attack silicon. Okay, and then once you have that form, you introduce your ketone, your titanium 4 chloride, and then what happens is that under these conditions, the enol ether is happy enough to attack. So the electrons come back down to reform the carbonyl. The pi bond of the alkene portion attacks the carbonyl carbon of the ketone, and that ketone itself is being activated by attaching to titanium 4 chloride. So you form this type of complex initially. And what happens now is that a chloride comes off from your titanium, and then that chloride ultimately attacks the silicon on the opposite carbonyl and has electrons come back to the carbonyl to give you your free carbonyl portion right here. And then at this point, you basically have an alkoxide that is associated with a metal. So all you do is you just quench it. You add water to this thing and you let the alkoxy group get protonated. And the titanium eventually will crash out as titanium oxide. Um, you'll be producing a little bit of HCl in the process as well. But if you use slightly neutral to basic conditions, then you can completely remove the HCl as water as well. All right, so that's how this mechanism technically works. Um, I kind of already mentioned that you could do this for the more substituted hydrogen. So now let me show you how that goes, and let me stop teasing you about it. So this procedure is even simpler than the one we did for the less substituted side. You used to do this at room temperature, but what you do is you first introduce a trimethyl chloride along with a weak tertiary base, and this gives you the more substituted enol ether, which then you can react with titanium chloride and the corresponding ketone to make your condensation reaction. So the way that this works is that when you introduce trimethyl chloride from the beginning, the carbonyl carbon is going to be silylated. Basically will attack silicon, the chlorine comes off, you make the silylated product right here. And here's where the tertiary amine base comes in. Basically, it's not apt to attack the carbonyl carbon because it doesn't have any protons to transfer and complete the process. So instead, it just acts as a base. And so it attacks the alpha hydrogen. The electrons come back here to form the alkene portion, and then the electrons of the carbonyl move over to the oxygen to form the enol ether. And from that point forward, the same reaction as before ensues, right? The enol ether attacks the carbonyl, which is already associated with titanium chloride. So the electrons move over from the pi bond to oxygen, and you have your interaction with titanium to form the complex here. The dissociation from titanium takes place, forming a free chloride, which then attacks via an SN2 reaction your silicon center right here. The electrons go back to oxygen to form the carbonyl, and at this point you quench this with water. Okay, so this is a very efficient process of making your beta hydroxy aldehyde or beta hydroxy ketones, and I would like you to use it in the future. So that kind of covers the first portion of this thing, regular aldol reactions with the same type of ketone or the same type of aldehydes. In the next video, we're going to talk about the cross aldol reactions, and we'll probably go a little bit further than that. So see you then. Bye bye.